Welcome. We're here to discuss the Gaia Catalogue of Nearby Stars. This was a science demonstration paper for the early third data release of the ESA Gaia space mission. Gaia is a large European project with over 500 scientists on the data reduction and even more for the technical and engineering aspects. The people shown on this page are the people who are involved in the making of the Gaia Catalogue of Nearby Stars, but this wouldn't have been possible without all the effort of the hundreds or thousands of other people involved in this product. On to the Gaia Catalogue of Nearby Stars, where we attempt to catalogue all stars within the solar neighbourhood. I hope you enjoy the trip. First off, a few quick, frequently asked questions. What is the Gaia Catalogue of Nearby Stars? We're hoping to catalogue all stars, all objects down to M8, within 100 parsecs of the Sun, that's 320 light years. Why is that important? This becomes a benchmark for understanding whether our theories of evolution and formation of stars and the galaxy make sense. They have to work inside our part of the galaxy. And it's difficult because there are many objects in Gaia, almost 2 billion objects, and if just a few of those objects, a few percent of those objects have erroneous solutions, then they might get scattered into our 100 parsec sample, as it were. So we can't just simply go and do a select. In fact, what we find is that if we just do a select on 100 on 10 mass, which is 100 parsecs, there are twice as many objects as we expect, and that's because there are objects that have erroneous parallaxes that have been moved into this sphere. So we have to use some clever way to sort those out, to understand what is a good object and what is a bad object.
Now, once we query the database for sources that are likely candidates to be within 100 parsecs, what we actually do is we select those that have parallaxes greater than or equal to 8 milliarc seconds. And when we do that, we realize that there is a strong contamination from spurious parallax solutions, which make sources fall in places of the color absolute magnitude diagram, which aren't physical. So what we do is we train a random forest classifier with examples of sources that we know for sure are good astrometric solutions by complementing Gaia photometry with 2-mass photometry, and sources which we know are bad astrometric solutions, just because in this case we take sources with parallaxes less than -8 milliarc seconds in the hope that they will have the same properties as the contaminants to our sample. We train the random forest classifier and apply this random forest classifier to the sources that we retrieve from the query to the Gaia database. We get a ranking of the variables that are most informative for distinguishing good from spurious parallax solutions. And then we analyze the properties of the samples, the resulting samples, when we change the probability threshold to separate one from the other. And it turns out that we find that a probability of 0.38 is optimal in some sense related to the ROC curve, which results in the sample that we use in subsequent sections of the paper.
Now that we have classified into good and spurious parallax solutions, we need to infer distances from our measured parallaxes. This is a classical inference problem, and for that we need to formulate our prior assumptions. For example, negative parallaxes are a perfectly fine measurement, but we don't expect any negative distances by definition. So here is our prior on distances. You see distances on the x-axis and the probability density function on the y-axis. And initially, we have cut on observed parallax of 8, so everything that is bigger than 8 milliarc seconds is included. And in the absence of parallax uncertainty, we would expect a steep rise until 125 parsec and then a drop. But since we have parallax uncertainty, even stars that are further away than 125 parsec can enter our sample. We generate this with a mock catalog that includes a galaxy model and the magnitude limits of Gaia and also an error model of the parallax of the parallaxes. Once we have this prior, and we use a very simple prior that is the same in all directions of the sky, we fold that prior we convolve it with the measurement, with the likelihood function, and this generates us for each source the posterior density function of the distances. And any source that has at least a 1% probability of being inside of 100 parsec is included in our Gaia catalog of nearby stars, which amounts to around 330,000 sources.
If we select all stars from Gaia EDR3 with a measured distance up to 125 parsecs from the Sun, the star number density projected on the sky, shown in the left plot, is highly non-uniform. The overdensity structures are mainly concentrated along the galactic plane and correspond to spurious astrometric solutions, which occur in crowded sky area when more than one object fall in the astrometric window of the Gaia detector, or can arise when the components of the closed binary systems are only resolved in a certain scan direction of the satellite. The first and most important task for the creation of a complete volume-limited catalog of nearby stars was therefore the identification of spurious objects done by the random forest classifier, which allowed to determine with high confidence the probability for a star of truly being inside a 100 parsec radius from the Sun. After cleaning, the resulting number density seen on the sky projection on the top right looks nicely uniform, as it is expected for the stellar content of the solar neighborhood. Another independent check of the performance of our classification was to examine the position of all stars in a color absolute magnitude diagram, which captures the relation between luminosity and color for stars of different masses and at different stages of evolution. We clearly see that the blue points representing good astrometric solutions trace the main sequence, the giant branch with its red clamp feature, and the white dwarf evolved sequence with a low level of contamination. And on the other hand, the bulk of rejected objects, the red points, fall in areas of the diagram which are usually empty, indicating that their parallaxes are unreliable. And this confirms the good sensitivity and robustness of our classification.
Another quality assurance test is to see how the catalog compares to the historical compilation of nearby stars. The figure on the left shows the number of stars in log scale as a function of distance in the GCNS compared to previous compilations. The Catalogue of Nearby Stars, CNS, was a large effort from last century to get complete census up to 25 parsec. The ESA Hipparcos mission has largely contributed in completing the census at large distances. The figure on the right is another graphic way to show the comparison. It gives the number of nearby stars within 10, 25, and 100 parsecs. The colors are representative for the catalogue with trigonometric parallax. The area of the circle is proportional to the number of stars. The circles overlap when the stars appear in several catalogues. It drastically shows the improvement of the census thanks to Gaia. The content has increased by a factor of about 2 within 25 parsec and 10 within 100 parsec. We believe that we know all stars within 10 parsec, as this is a zone of intense study for a long time. The before GCNS census contains 378 stars inside 10 parsec, and the GCNS found over 90% of those expected. Most of the missing stars in GCNS belongs to binary systems. The actual Gaia pipeline is right now only applying a single star solution. For the nearby objects in multiple systems, the non-single star motion induces large residuals and they have no correct full astrometric solution. This problem should be resolved with the next Gaia data release that will have multiple star solutions. However, an examination of the 10 parsec sample finds that GCNS provides the first direct parallax of 5 stars in multiple systems.
An important part of the characterization of the GCNS is defining both the completeness and contamination. That is, estimating how many objects we are missing and how many objects we are incorrectly including. often the minimization of contamination leads to a reduction of completeness and vice versa. They're completing ideas. Based on the 10 parsec sample, that is objects very close to us where we believe we are completely, we understand what's there. Our catalogue is 90 to 95% complete. We believe this is a worst case scenario because if we compare the catalogue to external comparisons, we have a higher level of completeness. Our formal contamination due to misclassification, that is giving a good solution when we should be giving a bad solution, is estimated to be less than 0.1%, but probably actual value is higher. Our estimation of the contamination from objects just outside the 100 parsecs is quite high, it's 9%, but that's because we've been very conservative and we provide a distance probability density function. So that error can be, statistically, can be completely accounted for.
So now that we have a volume complete sample, the 100 parsec Gaia catalog of nearby stars, what can we actually do with it? One nice application is the luminosity function, which counts the stars per magnitude bin per volume. And we have a 100 parsec volume here, so that should be quite good statistics. We use the magnitude limit, or we account for the magnitude limit of Gaia. That means stars that are fainter than the magnitude limit in a particular direction of the sky are not included in the luminosity function. And also the volume is lowered in that direction. And similarly, we also include the probability density function of the distances. So stars that are at the 100 parsec border only contribute partially to our luminosity function. You see the luminosity function here in absolute G magnitude on the x-axis. Bright stars are here, faint stars are here, and our sun would be around magnitude of 5. And on the y-axis, you have the number of stars per magnitude bin per volume. In red, you have the giant stars, and you see a clear peak for red clump stars. And for the main sequence, the luminosity function is peaking at around 11th magnitude. Then it goes down again for fainter objects. And what you see here is actually the stellar and substellar boundary. So you have stars to the left and brown dwarfs to the right. And this is really well seen in this, in this sample.
In a previous slide, we've shown how we infer distances from Gaia parallaxes. And we did that using a prior, which was based on Gaia Mo catalog. In this case, we're actually interested in inferring distances using a prior which takes into account the vertical stratification above and below the galactic plane, and which infers at the same time the parameters of this stratification. We do so by using the Einasto stratification law and also the more classical exponential law. And we do that including the effect of truncation, because our GCNS sample is actually truncated in observed parallaxes. This plot shows you the results for the entire GCNS sample as black contour lines. And for particular subsamples, in blue, for example, we have hot stars beyond the turn-off point. In green, we show the partial results for a smaller subsample of G and LK type stars. And in red, we show the results for the M stars. And you see there is a difference both in the degree of stratification and also in the position of the sun above the galactic plane when we use only smaller subsamples.
This sample allows to determine the peculiar motion of the sun, that is, the motion of the sun with regard to the stars around it. In this plot, we show the medium velocity of the nearby stars in gray, and we compare it with simulations where we assume different value for the sun velocity. So in blue, the sun velocity is assumed to be 12 kilometers per second, as it was determined about 10 years ago. Now we change the velocity of the sun in the simulation, and we obtain the green curve where the sun velocity is 6 km per second. And now the simulation is well in agreement with the data. So it shows that we have to review the sun velocity with regard to the nearby stars, and the value of 6 km per second is a much better fit than previously thought.
Ultra-cool dwarfs are some of the faintest things as seen by Gaia. They start at spectral type M7, or about 2700 Kelvin, and they go all the way down to room temperature objects. This includes both stellar and substellar objects. That turnover is visible in the luminosity function as shown a couple slides ago. That's about L3 is for turnover. M7 itself is complete for the whole catalogue, so 100 parsecs. Whereas by the time you get to L5, which is much cooler, you're only complete for the first 30 parsecs. At the far end, L8 and beyond, you're only complete for the first 10 parsecs or even less. We show here this histogram of the distance distribution of new ultra-cool dwarf candidates as found in Gaia EDR3.
The 100 parsec sample contains a number of stellar clusters. We looked at two of them, the open clusters Hyades and Coma Berenices. The Hyades are the closest open cluster, and thus particularly well studied. Our all-sky map shows our Hyades member candidates in red. We identified these in a two-step process. First, we identified stars with a common space motion. We used radio velocities from Gaia were available and also accounted for observational uncertainties and correlations. Our search is iterative to ensure that we are insensitive to starting assumptions. We also apply a spatial density filter to clean contamination from field stars, shown as gray dots. The figure includes a comparison with cluster members identified in the DR2 release papers. There, the analysis was limited to the cluster core. Blue dots are members we reconfirm, and green triangles are former members deprecated by our analysis. As a consistency check, we repeated the same analysis using the full unfiltered EDR3 dataset. We did not find evidence that the GCNS sample definition removed bona fide Hyades members, at least not in the core of the cluster.
The three panels on the left show the spatial distribution of the cluster members in galactic coordinates. The tidal tails agree well with simple n-body predictions overplotted in gray lines. However, the tails continue for many hundred parsecs, and the GCNS sample includes only a part of them. Color absolute magnitude diagrams show exquisite details, such as the sharp equal mass binary sequence and the white dwarf sequence. We did not apply any photometric filters in our membership selection. You can use our CAMD plots to understand how photometry filters could have been used for further cleanup. This is discussed in the GCNS paper, section 5.5, and in the EDR3 photometry paper by Riello et al.
Using the updated astrometric information from Gaia EDR3, one of the cases of exploitation for GCNS was to generate a list of wide binary systems. We adopted a three-step search criteria or selection criteria in order to define a list of resolved binary systems. This was based on the parallax differences, the proper motion differences, and the boundedness of orbits. And this resulted in a list of a total of 16,556 wide binary systems. And this includes rich open cluster members, such as the Hyades and the Coma Berenices, as well as young moving groups and higher order resolved multiples. We see no hint of a bimodal distribution, especially when we look at the log of the projected physical separation in AU, as shown in the figure on the right. And this bimodal distribution that could be expected from wide companions, such as those at 100,000 AU. And this is in agreement with the most recent results in the literature. Instead, in the figure at the bottom, we look at the wide binary fraction as a function of spectral type. As we can see, the F and G spectral types are rather constant, and this is also within the limits of recent results in the literature. The K spectral type shows a hint of a slight decline, and the N spectral types instead shows a sharp decline. This is likely to be real, And I would like to note that also for K spectral types, we are complete, whereas at M type, we are slightly incomplete at subspectral types greater than M7.
We also investigated unresolved binaries. They can be identified as overluminous sources above the main sequence. For equal mass binaries, for example, the source is twice as bright as expected for a star with that particular color. This is equal to a decrease in magnitude of 0.75. In the top left panel, we show the difference of sources to the main sequence in G magnitudes for the GCNS. We see an excess at minus 0.75, indicative of unresolved binaries. In the top right, we show a simulation of the main sequence without binaries. When using the prescription of RNU 2011 in the bottom right, the binary peak is too pronounced. Half of this prescription, as is used in the bottom left panel, seems to be about right.
And I am going to explain to you the white dwarf content in the Gaia Catalogue of nearby stars. Why are those objects so important? 95% of the stars end their lives as white dwarfs, and when they are converted into a white dwarf, they diminish a lot its brightness, and they are very difficult to be traced and observed from Earth. And only with Gaia, we are starting to have the possibility to have a complete sample in the nearby region around the Sun. And this is very interesting because it allows to recreate the past history of the Milky Way, because all these stars disappeared and converted to white dwarfs, track the evolution of the early stages of the Milky Way. So study these objects is quite important. And until Gaia, very few of them were only known. To identify these white dwarfs sample, then we use a random forest algorithm similar to what you have seen in the previous sections of the paper, but this time also using the photometry, not only the position, the distance and the proper motion, but also the photometry, the color and the magnitude of the stars, and also their uncertainties. Using this strategy, then we obtain about 22,000 white dwarf candidates. These random forests provide a probability of being a white dwarf. So these are the sample having probability larger than 0.5. And with this sample, we are able to build this complete luminosity function with a lot of details that were not previously seen in other studies. In particular, this region here seems to have a structure in the luminosity function, providing clues that maybe some burst in star formation is produced at this stage where these white dwarfs were created. That could be studied in more detail thanks to this sample. And also we detected that the bright peak here, the larger peak of population seems to be brighter than we thought before with previous studies. So these studies done with a complete population of white dwarfs in the nearby region then allows to detect more small features in the luminosity function, which is very interesting, and it proves that it's necessary to perform this kind of catalogs to have the most complete view of the Milky Way.
Can we make an even better catalog of nearby stars with Gaia? The question arises if, for example, you take a look at the color magnitude diagram depicted here and understand that some areas of this diagram are populated by most likely outlier or spurious objects that should not be in these regions of the diagram. The way to clean it up and to improve our understanding of GCNS content is going to rely on successful data releases for Gaia. Year 3, for example, in just a little over a year, will provide radar velocity information for maybe 50% or more of the objects in the GCNS. Astrophysical parameter information, including mass, radius, effective temperature information, will be available for virtually all objects. There will be, for the first time, known single star information content with the first publication of binary solutions in the spectroscopic, photometric, and astrometric channel. And there will also be new radio velocity spectrograph information in terms of, for example, time series of spectrum. Eventually, with DR4, when we will have the full astrometric data set available from the mission, we will learn about non-single stars in the solar neighborhood within 100 parsecs for essentially the full catalog available. And this information will also be used to improve the astrophysical parameters and all the information content available in the catalog.